Hello everyone. Today I will present you the use of drugs in World War II. My name is El MacDonald. I am an M.Pharm and Master Neuroscience student. This is the first part of this presentation. In this first part, I will give you an introduction on this topic. Then I will present what drugs were used and why using them and what were their effects on the brain. So World War II was a world war conflict which lasted from 1939 to 1945, and it opposed two major sides: the Axis, which appear in red on this map, versus the Allies, which appears on yellow. Why using drugs? Well, in World War II, these drugs were used to increase combativity by increasing alertness, by boosting up morale, making you more happy, and as a support in emergencies. What drugs were used in this purpose? Well, there was methamphetamine, or methamphetamine. So methamphetamine here was used as Pervitin in Germany, versus Benzedrine, which was amphetamine, which was used in the US and the UK during the war. Caffeine, which is found in coffee, but also in Germany was found also in chocolate, special tablets with cola nuts and chocolate. It's called chocolate, and both of these kind of drugs are what we call stimulants. They're making you more alert, making you more for methamphetamine, more boost up with more pep. For opiates, there was also opiates which were used, such as heroin or morphine, and it is found in a plant which is called Papaver somniferum. And alcohol. These kind of molecules, we call them depressants. That means that they're making you more relaxed, they're making you more a bit sleepy as well, but they're soothing you up in an event where you're feeling very stressed. So it's like more like a relaxation molecule, so to say. So, we'll see now what were the effects on the brain. So just going to give you a quick refresh on what were neurons, synapses, and the reward circuit. Then I will give you a presentation of the methamphetamine and caffeine effects, so the stimulants effects, and the effects of alcohol and opiates, so the depressants. So just a quick refresh. So the neurons are electrically excitable cells which transmit signals through the body. So here's the neuron communicating with another one, and so you have your cell body here, your nucleus, and the signal starts from here, goes through the axon here, the long elongated part, and then the signal goes to another neuron by the process what we call the synapse. These neurons have many roles. They're involved in movement control, sensors, and many others, and they're connected at other neurons, as I mentioned, with synapses. So we'll have a closer look of how a synapse works. So this is the synapse, substance-free. I mean, there's no drug having an impact on it. And here we're going to focus on the dopamine synapse. There are many other kind of synapse, but here we'll focus on an important synapse, which is dopaminergic synapse. And the dopaminergic synapse is actually involving dopamine. Dopamine is what we call a neurotransmitter molecule. So it is a molecule which is a sort of like a messenger signal, which is like a messenger. And when the neuron here, presynaptic neuron, and the postsynaptic here, when the presynaptic neuron is depolarized, so there's like electric current going on, then this little bubbles here release dopamine, and this dopamine is going to be then given to receptors there, and this will give a signal to a postsynaptic neuron to be activated, and so on and so on. So I'm going to show you with animation how it works. So your electric signal, release of dopamine binds, creates electric signal to a postsynaptic neuron, and goes on and goes on and goes on. So dopaminergic synapse is involved in the sensation of reward, and it's causing a reward sensation. So it's a neurotransmitter molecule which is giving you the sensation of pleasure, of reward. And so also what happens is when the dopamine is released, a part of it is binding to the dopamine receptor, another part of it is actually recaptured related to the presynaptic neuron, so it's recycled. That way there's no waste of dopamine. we'll see that this is really important because drugs can modify this behavior, can modify the binding to the postsynaptic neuron, and can modify the recycling of the dopamine molecule. So dopamine actually is involved in what we call the reward circuit. So here you have a soldier which is drinking alcohol. So let's have a look of how it works in his brain. So the reward circuit is made of three different zones. You have a frontal tegmental area first, which stimulates the reward center, which is the nucleus accumbens here. And then you have a prefrontal cortex, which is involved in decision making. All of them interact together. What happens when you have alcohol? Well, alcohol hits the frontal tegmental area, creating a massive release of dopamine, creating pleasure. And this has an impact on the prefrontal cortex, which is going to have a behavior reinforcement. So every action we do normally are involved by the release of dopamine. And when we have a pleasure of doing something, then we're going to learn and we're going to think, oh, that's really good. So every time you'll be in a decision making involving pleasure, then you have your cortex is going to act on this and is going to act on whether it should control or not this behavior. And here what happens is that with alcohol it reinforces the behavior of drinking more alcohol because it gives you more pleasure, and so on and so on. So it's like a circle. Okay, so we saw what were effects of, so what are the dopaminergic synapse, what is the reward circuit, and so now we'll see what are the effects of drugs on this circuit, and specifically methamphetamine. So what happens is that amphetamines or methamphetamine have a really high similarity to dopamine, which is here. You can see it really looks very, very much alike. And because it's very similar, it's going to take the place of the dopaminergic receptor. And so it's going to also go enter the synaptic neuron, be released as dopamine, and bind to the dopamine receptor and create also the sensation of pleasure. However, it's going to stay much longer than dopamine, and so it's going to have a much longer effect. And there's also one thing as well, is that it's going to compete with the dopamine cellular transporter, so the dopamine recycling transporter, so the dopamine transporter which is like taking back dopamine to recycle it. And what happens is that it's going to compete with it. Can show you again the animation. And it's going to compete with it, and what happens is that the dopamine is going to stay longer in the synapse, and it's going to create a lot of pleasure because it's going to bind to a lot of dopamine receptors at the same time, more than usual. So this creates a lot of sensation of pleasure. It also boosts up synergy and confidence, and it removes fear and pain, and for amphetamine the effects can last up to 4 hours. It is highly addictive, however, there's a risk of cardiac arrest risk, and also there's at least 2 or 3 days of recovery which are needed after intake. Also, one of the negative effects is that you cannot sleep because it's making you so much alert that you cannot sleep for at least 24 hours. As is really strong. For methamphetamine, the effects are the same as amphetamine, however, they're longer. They can last to 8 to 12 hours, and for same thing for the side effects, it is also longer. Okay, so now let's have a look at the other, and they're gonna change. Oh, so caffeine. So caffeine is totally different. Caffeine is gonna not work on the dopamine synapse at all. It's gonna work on the adenosine receptor and adenosine synapse. So adenosine is a neurotransmitter as well, which is involved in making you binding to adenosine receptor, and is involved in making you sleepy. What happens is that caffeine here is going to take the place of adenosine at the adenosine receptor. So it's going to be an antagonist. And so what happens here on this picture is that caffeine binds to adenosine receptor. Adenosine cannot bind to its receptor, so it has no effect. And if it has no effect, then it's not making you sleepy anymore. And so that is the role of caffeine. It removes sleepiness by taking the place of adenosine. So it is not involved in pleasure directly, so to speak. It has a totally different action. It's just making you more alert. So it boosts up synergy and it boosts up thinking. One thing is that it only works on 2/3 of people, and subjects can be a bit jittery after too much intake. However, it is not as addictive as methamphetamine, and also, of course, it has done the same side effects as you can see. Okay, so we saw the two different stimulants. Now we're going to talk about depressants, so alcohol, as I mentioned before. So this is just a more detailed view of how alcohol works. So what happens with alcohol is going to inhibit the inhibition of neurons, which are normally inhibiting the release of dopamine. So what does that mean? Alcohol is going to work here on this neuron pair, and it's going to inhibit GABA interneurons, which are involved in inhibition of this neuron here. And so what happens is that by inhibiting the inhibition, you're doing an activation. So what happens is that these neurons don't have any inhibition anymore. So what happens is that we're going to send a lot of dopamine in the nuclear accumbens, giving you a lot of reward, sensation of reward. So it has anxiolytic effects, euphoric, analgesic effects. So it's removing the pain, it's making you more happy, and it removes the stress. However, there are negative effects. Creates motor and cognitive impairments when you're drunk. Well, you're not really good at doing a Rubik's cube, for example, or standing up just simply. So it's not really a lot. It's this kind of like negative effects. Also, you have in the end neurological toxicity, and it's highly addictive as well. Okay, so now finally, what about morphine or heroin? So it's also a depressant as well, as I mentioned before, and the effect is more or less indirect. So what happens is that in this animation here, the morphine heroin compound is going to bind to actually the opiate receptors, creating a massive release of dopamine, and it's going to give you a lot of pleasure and sensation of reward. And so what happens is that it has, so as alcohol has analgesic, euphoric, anxiolytic effects, and it can last up to 4 to 6 hours for morphine. It has also some negative effects. It's highly addictive if misused. There's some severe withdrawal effects. Um, Also, it could create insomnia, and if overdose can be sometimes fatal. For heroin, the effects are similar, and it's actually more addictive than morphine because the duration of the action is shorter. I should just point out that morphine is highly addictive if misused. What does that mean? A lot of people just commonly think that morphine is you're gonna be a drug addict if you use morphine for as a painkiller, for example, and this is partly true in the case where morphine dosage is much higher compared to the pain you're supposed to treat. If the pain amount and the dosage of morphine are matching together, then there is very, very little risk of addiction. Just wanted to point that out. Now, okay, so we saw reaction of all of these drugs on the brain, and if my slide wants to move on and it's taking a sweet time, and it's not doing so. Okay, so now we will see how these drugs were used in different countries involved in the World War II. So Germany, Finland, Japan, and then also about the Allies, so the UK, the United States, and the USSR.